Okay, here we go. Here's lesson 2.6. Video notes prove geometric relationships. So we'll keep rolling with some of those geometric proofs. We'll look at a couple new um, postulates, theorems that maybe help us along the way, but it's still kind of all centered at proving geometric statements. Okay, so let's run through it. It's not an overly long lesson, but let's do it right. Let's hit all our a quick review on some vocab for us. So first thing here, this was covered in lesson 2.1. The definition of perpendicular lines says that if two lines intersect to form a right angle, then they are perpendicular lines. And it came up then, we were talking about if-then statements. So that's how it's written. If two lines intersect to form a right angle, if two lines intersect to form a right angle, then they are perpendicular. The converse is also true. If any two lines are perpendicular, then they intersect to form a right angle. So that's the connection we basically need to make, is between when I hear or see perpendicular, I see, or I think, I write right angles. Right angle, perpendicular, that's what goes together. This one's come up already a few times, lesson 2.5. The definition of congruence, or definition of congruency, definition of congruent angles, congruent segments. For us, it's really a converter. It converts between angle measures being equal, so equality, to congruence. Angle A is congruent to angle B. So we talked about this in the previous notes. See lesson 2.5 for that review. In general, one of the things that we're a lot of times doing with these geometric proofs, it's a good kind of rule of thumb, is try to get everything into equality, because then we're able to substitute, we're able to use the transitive property of equality, stuff like that. So it's a lot of times if we have a mismatch of congruence and equality in different statements, a good rule of thumb is try to get everything to equality if we can. So that's where this one comes in for us. One other just thing to review here before we kind of get into it is some of these terms that have come up and really in chapter 1. So complementary and supplementary angles. Basically, any two angles that add up to 90 is complementary. Any two angles that add up to 180, whose measures, right? We're talking about their measures. So the measure of angle 5 plus the measure of angle 6 equals 180 degrees. So we're talking about measures being equal, whether it's complementary, not equal, but adding up to 90 or adding up to 180. I think hopefully those ones are ones that we're solid with. Ones that maybe were newer from, this is lesson 1.6, a linear pair. I know it's kind of small here, but a linear pair is adjacent angles. So remember, adjacent means sharing a vertex. They're sharing this vertex right here, sharing the side, and their non-common sides form opposite rays, or we could also say that are supplementary. Vertical angles then, we said originally, think of the letter X. So right here I'm seeing that X formed with these two lines, and we kind of said that it's not super formal, but that vertical angles are on opposite sides of the X. So 4 and 5 are vertical angles, and 3 and 6 are vertical angles. So just reviewing some of that vocab, because it'll come up here as we get into some of our geometric proofs. Okay, so the first thing we add to our notes, kind of new material. I know it says review here, but kind of reviewing notes from the book. A new theorem for us, actually our first theorem of the year, the right angle congruence theorem. So abbreviation-wise, if we want to abbreviate, which a lot of times we do, we'll use the right angle congruence theorem. Okay. A theorem, remember, is just something that is formally can be proven. It has been proved using kind of the process that we're kind of learning about right now, versus a postulate isn't able to, there's not enough information to actually prove it completely. So that's kind of the difference. Don't get hung up on between what's what. For the most part, we're not really worried too much about which one's a theorem, which one's a postulate. So what this says is basically that all right angles are congruent. I think it's kind of like a postulate in the sense that these are usually a postulate is something that's very intuitive, or very what a lot of us might say is like, yeah, of course that has to be true. If I've got a right angle, I've got 2 different or 3 or 4 or 5 different right angles, I know they all have to be congruent. That's what this is saying. So what does this look like in a proof? It could look something like, and this is just really informal here, but obviously, we would start a proof with some given information. We don't even have to be super specific there. As it was given, this is that. Okay. But usually how this works is we have to establish that we have some right angles. So however we get to that information, like angle X and angle Y, actually using words, angle X and angle Y are right angles. Okay. And again, that could come through a variety of ways. So the reason here is kind of tough for me to just nail down one that we would know that. Sometimes that just is told to us, it's given to us. Sometimes we might see it in a picture that would also kind of fall into like a given category. We could potentially use the definition of perpendicular, right? So if we go back to our review of perpendicular lines, we would see maybe we were told two lines, I can't even see them here, line L and line M are perpendicular. Okay. So this angle right here has to, we could name it angle X or angle whatever, has to be a right angle because of the definition of perpendicular. So something along those lines. So like I said, it's hard for me to pinpoint this exactly what a good reason is always going to be as to how we know something are right angles. But definition of perpendicular, given information. And then once we establish, this is kind of the big takeaway here is, in a second step, after I establish that I have right angles, we could definitely say that angle X is congruent to angle Y because that's what our theorem said. It said all right angles are congruent. So basically we need to establish that we have some right angles. And then later on in a second step, wherever I need to, or if this was something I needed to state, I could say that angle X and angle Y are congruent because of the right angle congruence theorem. All right, so that's kind of how that would get used in a proof. We'll do one. So if you're feeling like, what the heck, there's no picture here, this was just kind of me showing you how a little bit of the mechanical behind it, where you have to kind of say you have right angles first before we can say, oh yeah, now they're congruent by the right angle congruence theorem. All right, let's take a look at some pictures here. I think this is it's a nice 3-step, shorter proof. Remember, going through that process, that's the part that we really got to work on building is this process, this top-down approach of how do I get from beginning to end. So it's kind of like a little bit of a road trip. I think I made that reference in the previous lesson. So let's start. I think hopefully by this point, everybody knows where to start it. I got to be careful that I'm not just like blindly copying the given. So let's say segment JK is perpendicular to segment KL. It's good to say it to myself. Obviously, I'm saying it out loud here. And then segment ML is perpendicular. That's what that symbol means. So there's still stuff there that I got to interpret, and perpendicular to KL. We know that that's given. But then I do want to take a step back and, okay, what did I actually write? I was kind of just copying this down. And what did we actually say? We said segment JK. Where's JK? It's right here. That's perpendicular to KL. So it is marked in the figure, but I think for me it's helpful to kind of highlight that, okay, hey, if that's perpendicular, what did perpendicular say again? And that's why we reviewed it right here. If lines are perpendicular, then they intersect to form a right angle. So that's telling us that it's okay to put that little marking there. And then similarly, it tells us that segment ML is perpendicular to segment KL. So again, that tells me that it's okay to put a little right angle symbol there. So what are we trying to prove? Remember, this is always like this proof statement is where our destination. We want to get there. I need to say something about angles K and L. So I haven't said that, right? Like, this statement 1 just says a couple segments, some segments are perpendicular. Okay, we need to introduce this angle K and L to the proof. They can't just show up magically on the last step. So this is what we had just talked about, that I need to establish, like using words, using a sentence, and say that angle K and angle L are right angles. That's new information that was not stated earlier. We kind of marked it in the proof, right? We highlighted the right angle symbols, but this statement did not say anything about right angles. JK is perpendicular to KL, ML is perpendicular to KL. Right angle does not come up there. We're applying some knowledge to come up with this. How did I know that so that's angle K and angle L are right angles? How do we know that? Because we know what the definition, I've referenced it a few different times, the definition of perpendicular says. I could click back to it. I guess it says lines are perpendicular, then they intersect to form a right angle. Lines are perpendicular, all right, segments were perpendicular, they intersect to form a right angle. Okay, so now I've said something about angle K, I've introduced it, I've introduced angle L into the proof, they're there, we've established the right angles, we justified it using a good solid definition. The last thing, all right, is, all right, are we able to say this now? Can I say that angle K is congruent to angle L? Well, absolutely, right? It goes back to the note we just took. How do we know they have to be congruent? Because we said every right angle has to be congruent. That was the right angle congruence theorem. All right. So kind of a short proof, right? Obviously, our statements 1 and reason 1 should have been just a slam dunker. We know that one. We know kind of where it's going to finish. It was just a matter of getting that established like we had talked about, okay? So that's how we would potentially use the right angle congruence theorem. All right, let's talk about 2 other ones. You can kind of see is where we're going. We've got slide 7, slide 8, slide 9. There's not a whole lot left. Two other, well, a postulate and a theorem. So let's do them kind of one at a time. We'll probably do the same thing. The first one's called the linear pair postulate. So definitely add this to your notes. This is something we'll use. If 2 angles form a linear pair, then I know the angles aren't congruent. So 1 and 2 are forming a linear pair. They are supplementary, right? Because they, there's different things we could say because of the straight line or this straight angle right here. Those angles would have to be supplementary. And then this is kind of saying it, so then after the fact, I could definitely say that angle 1 form a linear pair, so 1 and 2 are supplementary, which means that measure of angle 1 plus a measure of angle 2 equals 180. So that's the part I was going to kind of add like as a second part to our notes. What would this look like in a proof? Let's take a look. So something kind of like the last one where I just, real informal, just, we're going to have some given information, right? No matter what it looks like. All I have to do is see in a picture. Let's use some different numbers, angles 3 and 4. So I see a picture that looks like this, and I'm, based on my proof statement, I feel like it would be beneficial to say something about angles 3 and 4 being supplementary or being, measures equaling 180 or something along those lines. So as long as I can see it in the picture, all right, I could definitely say that angle 3 and angle 4 are, can we squeeze it in here, supplementary. And that's exactly what our linear pair postulate says. It doesn't say anything about 180. So here's the actual linear pair postulate. 2 angles form a linear pair, then they are supplementary. That right there is a linear pair postulate. Okay. 3 and 4 are supplementary. I can see from the picture they're forming a linear pair. So that would be the linear pair postulate. All right. It's come up a couple different times already, but we said a lot of times, like this is a word sentence, right? 3 and 4 are supplementary. It's not bad. It's good. It's true. But for our purposes, for a lot of these proofs, a lot of times it's nice to have an equation. We said that's a good rule of thumb, is try to turn stuff into equations so we can substitute. We can use a transitive property if necessary. So a lot of times, if after we use the linear pair postulate to kind of introduce maybe angles 3 and 4 into the proof, it's usually pretty beneficial to say the measure of angle 3 plus the measure of angle 4 equals 180. Now we're down to an equation where I might be able to substitute something in for one, for 3, if I knew, in the given that angle 1 was congruent to angle 3 or something like that. But how did we do that? I still need a reason for that. It's because of this word right here. What does supplementary mean? That's why we reviewed it again. 2 angles are supplementary if their measures add up to 180 degrees. So the definition of supplementary would be, converting us from these words, this sentence, to a mathematical equation. That's maybe a little bit more useful. All right, so that's a very common, kind of a 1-2 punch there almost, where we would establish we're supplementary by the linear pair postulate, and then usually soon after we'd want to turn it into an equation where we could work with. Okay, so there's our linear pair postulate. We'll look at, I can't remember the example. We'll see if it comes up in this example. It's either that one or this one right here. So let's add this to our notes. The vertical angles, we'll just call it the vertical angles theorem, the vertical angle congruence theorem. You could abbreviate this one, the vertical angle theorem. Don't do VAT, just say VA theorem, the vertical angle theorem. It's short, it's sweet, it's to the point. It says that all vertical angles are congruent. This one's pretty useful. It comes up a lot in chapter 3, as well as obviously some of the proofs we're going to do now. And it kind of works the same way, whereas all I have to do is see it in a picture to say, hey, you know what? If I need to state right now that angle 1 is congruent to angle 3, I can say that kind of out of the blue. I don't need any other lead up to it. I could say that because that's what the theorem says, that vertical angles are congruent. Angle 1 is congruent to angle 3. So let's just do that one more time, where we kind of just do a generic proof, something how that would look. Got some, who knows, again, this is just to give an example of how it might show up in a proof. I need to see the picture of it though. Okay, this is one that I know some proofs we do more than others. Let's do 1, 2, 3, and 4. It doesn't matter, same numbers. But I know some proofs we do, we don't really use the picture a ton, but if the vertical angle theorem is something that I need to see it to be able to use it. So I could absolutely introduce right now, for, depending on what I was being asked to prove, if I needed to, if I felt like it was helpful, I could absolutely say that angle 2 is congruent to angle 4 by the vertical angle theorem. All right. Now again, it's congruence, which isn't bad. That's not a terrible thing. We've introduced 2 and 4 into the proof. Maybe that's helpful down the road. One last thing that we might do, I'm not saying you always have to do this, but depending on what we're being asked to prove, it might be helpful to say, you know what, congruence is great, like we have in step 2, but we're not able to substitute with congruence. We need the substitution works with equality. So I might need to convert from congruence, right? We lost the squiggle here. That means congruence. We lost the squiggle, but then we gained the little m's. Okay, so how do we convert? That was our third thing that we reviewed, the definition of congruence, or definition of congruent angles. So that's common. I'm not saying that's an always type of thing, but that's a common thing that would happen. We would convert from congruence to equality to allow us to keep working with it, okay? All right, enough build up here. I think we've got one more proof to look at. And there's a lot going on here, but I think if we take a step back and just kind of, again, keep working on our approach, not like make it a fill in the blank proof, but all right, what's being stated? Where am I trying to get to? Let's take a look. I'm going to do kind of the blind copy of the given. Again, it doesn't hurt to say it to ourselves. Angle 4 is a right angle. That's pretty straightforward. That's given. And then now let's take a step back and just, all right, is that marked? If it's not marked, I'd mark it. It is. I'm still going to highlight it and just say, okay, angle 4 is a right angle. There it is. That's good to know. I got to look at my guide. Here's my roadmap. We got to get here. That's our destination. I guess we're going to build the roadmap of how to get there, but that's what I need to say. Angles 2 and 4 are supplementary. Let's see. Let's just, on the surface, is that true? Well, let's see. If 4 is a right angle, which I know means measure of 90 degrees. This vertical angle over here we just got done talking about, and here's the hint, we're going to use the vertical angle theorem. But, I mean, just talking through it, sure, if 4 is 90, 2 has to be the same, 2 has to be 90, those are vertical angles. And I know what supplementary means. It means 90 plus 90 equal, or it doesn't have to be 90 and 90, but any 2 angle measures that add up to 180. Well, 90 plus 90 is 180. So absolutely, I think we can do it. We basically have to kind of go through what I just very informally talked through and kind of lay it out in a more of a formal situation. So let's take a look. I see 4 as a right angle. That's good. 4 needs to be mentioned. It is mentioned right now. At some point, we're going to have to get 2 involved. Let's take a look at kind of where this is going. The only thing I'm not a huge fan of the fill in the blank ones is it kind of forces us to do it a certain way. Like right now, we have to apply the definition of a right angle, which, let's see if I can jog my memory. The definition of a right angle is a measure, or an angle whose measure is 90 degrees. So if this is being told like you have to use this, it's basically saying you have to apply that. This is getting applied right here. So instead of saying angle 4 is a right angle, what are we going to say? We're going to say the measure, oh, what happened to that green? The measure of angle 4 equals 90 degrees. There we go. It's happened now, I think maybe the third time, well, it's at least been mentioned a few times that it's nice to have things in equals. Go from a sentence to equality. Okay, the definition of a right angle, we all know that. It means 90 degrees. Great, the measure of angle 4 equals 90. All right, let's get working on this 2 now. 2 is not in my proof. Statement 1, statement 2. I haven't talked about angle 2 yet. I think this is a great time to start talking about angle 2. So we said, okay, without a doubt, for sure, angle 2 has to be congruent to angle 4. How do I know that that has to be true? Because they are vertical angles, and vertical angle theorem says, yep, they got to be congruent. So let's add that one. The vertical angle theorem says this must be true. Great. So I'm looking at my most recent statements. 2 is congruent to 4, and I'm kind of noticing, hey, there's a mismatch here, right? There's this mismatch of formats. This one's talking about congruency, and this one's talking about equality. So here's where I said on the last one that whoops, maybe it wasn't this one, the vertical angle one, that a lot of times it's nice to go from congruence to equality. We're seeing it show up right here. Let's go ahead and convert this right away. We're going to use the definition of congruence, or the definition of congruent angles, and turn this statement in step 3 into the measure of, whoops, not 3, what am I doing? The measure of angle 2 is equal to the measure of angle 4. There we go. Where's our two most recent statements? So I've got this one that I'm still kind of keeping in my back pocket, right? We kind of dealt with it from step 1 to step 2, and we haven't really done anything with it yet. We introduced new material in statement 3, and then we said, you know what, let's get everything in the same format. So I'm not saying you have to circle, and I really wouldn't want you necessarily to circle, but I want to make sure as we're kind of seeing these proofs here that, okay, that's where I'm focused now. I kind of use this. It helped me. It got 2 in the proof. I converted it to equality. Let's see what we're talking about. We said 2 and 4 are equal. 4 is 90. I think the next thing we want to establish is 2 being 90. We haven't said that yet. We know 4 is 90 because we were told it was a right angle. We know 2 and 4 are the same, so I think one of the next things we want to say is, all right, the measure of angle 2 also has to be 90. So we're kind of combining these two statements. 2 and 4 are equal. 4 is 90. So, of course, measure of angle 2 has to be 90. This is one of those ones that you actually end up, there's 2 ways you could justify this. Some people see this as a transitive property, which that's kind of how I see it. I see the measure of angle 2 is equal to the measure of angle 4. That same measure of angle 4 is equal to 90. So we could kind of like cut out the angle 4. You cut out the middleman, the overlap, and just say the measure of angle 2 equals 90. So that would be transitive property of equality. The other thing that we've done a lot in class is straight substitution. Hey, 2 is equal to 4. 4 is equal to 90. So wherever I see a 4, I'm going to replace it with something that 4 is equal to and just shove this 90 right in there. And that you could argue that as well. So I think either one is totally valid here. Don't say both. Just pick one. Let's go with the last one I did here was substitution. So I'm going to say the substitution property of equality is kind of where we got. All right. So let's see what we're working with here. Our 2 most kind of recent statements, they're not most recent, but I think the most useful ones is we've established for sure that 2 is equal to 90. We still have this one here that 4 is equal to 90. So 2 is equal to 90, 4 is equal to 90. I haven't looked at my proof statement in a little while. We want to say that 2 and 4 are supplementary. So I need to add these 2 together. This next step 6 here is a little bit weird. It's kind of coming out of nowhere. I'm just kind of making a blanket statement that 90 plus 90 is 180. All right, you could check that out, but I think hopefully that's the one that 90 plus 90 equals 180. That's kind of coming out of nowhere a little bit. But it's also the definition of an equation. Like that's the left side of the equation is equal to the right. So 90 plus 90 is 180. The reason that I kind of need to say that there is because I'm basically looking for a place that I want to substitute these things in. So let's clear a couple things here. I just want to kind of clean this up so it's maybe a little easier to follow. So what's circled in black are kind of the big statements that I have left. And this is going to be a straight substitution. So I'm going to take this kind of generic statement. I would give you something like this. This is a weird one that I wouldn't expect everybody to kind of know how to do something like that. But I've got 90 plus 90 equals 180. And my next statement, what happened? I said, all right, these two ones that I've got circled, highlighted in black, those are my big statements. Those are our useful ones. So I'm going to say, you know what? I'm going to replace U90 right there with something that you're equal to. I know 90 and measure of 2 are the same. So I replace that 90 with the measure of angle 2. Very, very similarly, we said, hey, you know what? I can replace this 90 right here with something that 90 is equal to. 90 is equal to the measure of angle 4, so let's throw that in there. So now my new statement reads the measure of angle 2 plus the measure of angle 4 equals 180. How did we get from, kind of step 6 to step 7? That is another example of substitution property of equality. Okay, we replace things that were equal. I think, if I take a step back and look, it's kind of hard because I keep scrolling here, but what did we want to say in the end? What were we trying to say? That 2 and 4 were supplementary? I think we're really darn close right now. Like we've said that when we take the measure of 2 and the measure of 4 and add them together, we get 180 degrees. That's pretty much what it means to be supplementary. Not pretty much, it is what it means to be supplementary. So the last thing we got to do is go back now from this mathematical equation. Let's turn it into words. How do I know that? Why am I allowed to say that 2 and 4 are supplementary? Because that's literally what supplementary means. Supplementary means two angles that add up to 180. I'm directly applying the definition of supplementary. All right. So we're able to use that to convert back then from an equation to words. Okay, so we kind of used the definition of a right angle early on to convert from words to an equation. We can work it back the other way. I know it's not the same definition, but go from an equation back to words using definitions. Okay, kind of a beast, kind of a long one there. A fill in the blank one for now. For the most part, that's kind of where we're at. We added a few new justifications today. Let's finish with something that hopefully everyone says is, oh, okay, that's a little bit more doable. And we'll talk about why it's showing up here. So we've got a figure here, some expressions, 5y plus 2, 5x minus 7, and 113. And it's basically what we're being told to do is just write and solve an equation to find x. Write and solve an equation to find y. So there's no justifications here. There's no... I'm not asking you to write a proof or set up a 2 columns or anything like that. We could, okay, but I'm not asking you to do that. So here's what this would look like. I'm kind of looking at the picture. There's actually a lot of different ways I could do this. Obviously, it's kind of nice to have, like, this 113 is a nice angle to have here just because it's exactly 113. Some people look at this and say, I kind of wish I knew what this one was over here. Well, we can find that though, right? Because if, what I've kind of highlighted in blue is a straight angle, a linear pair from, angle GJH and angle H, I think I said it wrong, GKH and angle HKJ. So these two angles right here and here are a linear pair. We said had to be supplementary. So I could just do 180 minus 113 and say, you know what? This is a 67 degree angle. All right, I subtracted 113 from 180, and that's where I got. The reason that might be helpful is now I have 2 different sets of linear pairs. I'm sorry, 4 different sets of linear pairs, but 2 different sets of vertical angles. And remember, our big thing that we just kind of added today was vertical angles have to be the same. So maybe I want to start with my y, the way I wrote it. I could say that 5y plus 2 has to be equal to what we figured out to be 67. Okay. And again, if this was a justify, I would say, well, how do you know that that's true? Because the vertical angle theorem says that has to be. So But again, I'm not asking us to do that. It's just I'm looking for you. I'm trying to give us some opportunity to use our algebra skills in line with some of our new geometry concepts. Okay, so that's definitely a setup I could go with right there. I could also, well, let's solve it. Let's subtract 2 from both sides. I'm applying the subtraction property of equality. I'm not going to write that out, and I'm going to divide both sides by 5. The division property of equality to get y equals 13. Okay. That same approach I could do. Does anybody see it this way? Where I know what that one's done. So if you're like, why are you still doing it? Could I go 5y plus 2 plus 113 equals 180 degrees? If I start talking about this linear pair from right here to here, sure, that's another 180 degrees. So why couldn't we add 5y plus 2 plus 113 and set it equal to 180? So there's multiple ways we could get to the same spot. I guess I'll take that off there just because I know I'm going to run out of space. But definitely a different setup we could look at. I think to find my x, I'm going to use the exact same process. I'm going to look at this vertical angle right here that I've marked in orange, so angle FKJ, and say, you know what, that's a vertical angle with GKH, this one right here. Those have to be the same. 5x minus 7 has to be equal to 113 because of the vertical angle theorem says so. So I'd add my 7 to both sides, the addition property of equality, don't have to state it. And I would divide both sides by 5 to figure out that x equals 24, I believe, on that one. And that's it. Did we do what it asked us to do? It said write and solve an equation to find x. Absolutely. It didn't say anything about justifying anything. We're good. It asked us to write and solve an equation to find y. Yep, we did that. We're good. And look at that. We are out of slides and proof. So, I mean, in the end, what was it? We did 2, kind of one longer proof, one shorter proof. We talked a little bit about just some generic setups and how we might use the linear pair postulate. That's the only thing we didn't see here today. I feel like I'm second guessing myself, but no, I don't think we ended up using it. Where it could potentially work here on something like this, or if this was a proof, we could definitely do something along the lines. I took all my my black ink off there. Sorry, just if you wanted to see like a setup, if I wanted to say the measure, I could say like angle. It's really hard because I can't see my letters here. GKH, so angle GKH and angle GKF are supplementary. Okay, so I'm talking about this angle right here and this angle right here being supplementary by the linear pair postulate. That's an example of how I might use that in a proof. And then later say, the measure of GKH plus the measure of GKF add up to 180 degrees because of the definition of supplementary. I know I'm maybe confusing you. We did it. We kind of laid it out here like this. Okay, so that's kind of how it would come up in a proof. I wish I should have set up an example for us to do with that one. But in the end, I think that's kind of what we needed to get through. We're still doing those geometric proofs. We looked at a couple different ways using different special pairs of angles, linear pairs, vertical angles, and even complementary and supplementary to help prove some of those geometric statements, converting words, sentences, all that good stuff. So, yeah, I think we can call it. Let's call lesson 2.6 notes done. That's what we did in class. Yeah, I will look forward. I'll look for you, and I'll see you in future lessons.